Hi, in this video we will give an introduction to simulation in LabVIEW. The software you need in this video is LabVIEW and the LabVIEW Control Design and Simulation module. This module is used for creating control and simulation application with LabVIEW. Here you will find PID controllers, etc. And the module is available as a palette on your block diagram when you have installed the module. LabVIEW and the control design and simulation module can be downloaded from this website. Here is a short overview of the contents of this video. We will learn how to simulate block diagram in LabVIEW based on differential equations. In the beginning we will use the simulation loop, while later we will also introduce and use the ordinary while loop. We will use and learn how to use the PID functions that are part of the module, and we will create simulation and subsystems, and finally we will create a simulation system using the while loop with a subsystem inside. So what is LabVIEW? LabVIEW is a graphical programming language. It's very different from traditional programming language like Visual Basic, C#, Maple, MATLAB, MathScript, etc. So MATLAB is basically more like a drawing program than actually a programming language. So everything you do, you draw it instead of program it using a text language. This approach to programming makes it very easy for those who are not programmers or for those who don't like programming in general. So this makes LabVIEW an excellent tool when using hardware, when you need to take measurements, etc. LabVIEW is created by National Instruments, and National Instruments also create lots of hardware that you can use together with LabVIEW. All this makes it very fun, and you become very creative when doing LabVIEW. Here we see a typical LabVIEW example. So the code window is called the block diagram, and inside here we place graphical objects and we wire them together to create the flow in the program. So just like ordinary programming like C#, etc., we have while loops, for loops, etc. So this is actually a while loop. Local variables and global variables we have. So this is an example of a local variable. We use or can make our own functions or methods, but in LabVIEW we call it sub-VIs, like this. Here you have a case structure, which is like an ordinary if-else sentence in ordinary programming languages. Here you see an example of an array. Here you see an example of a constant. You can also use comments like this, etc. We have also the possibility to set properties, and then we use something called the property node. Every time we need to do something with these objects, we can right click on them, and then we get a menu where we have lots of options for each objects. In this case, the while loop is connected to a stop button, so when we click the stop button, the while loop stops and our program stops like this. Every LabVIEW program consists of two windows. One window, which is what we call the front panel. In this window you create your graphical user interface, while in the block diagram is where you create your code. So every program consists of these two windows, and those two together are saved in one single file, which ends on the extension .vi. VI stands for Virtual Instruments. You can easily switch between those windows using the shortcut Ctrl E. In order to create our graphical user interface, we use the so-called controls. So when you right-click on your front panel, you get the controls palette. Here you find all the objects you need to create your graphical interface. While when you are in programming mode in a block diagram, and if you right-click on the block diagram, you get the functions palette. So here you find lots of built-in functions you can use. Here you find different loops. Here you find numerics. Here you find boolean, arrays, string functions. If you want to save something to file, etc. So basically we find everything we need here in order to create our program. LabVIEW consists of several modules. So we have the LabVIEW basic environment. In addition, we can have install one or more modules. The most used modules, or the typical modules, are listed here. So we have the LabVIEW math script module, which is very similar to MATLAB. And the module we are going to use in this video is the LabVIEW control design and simulation module. If you want to integrate hardware inside your application, you need to install the NIDAC MX driver. Since this video is based on modeling of dynamic systems inside the LabVIEW environment, we will just give a short introduction to modeling of dynamic systems. Here we have some examples. Here we have a water tank, and here you see the mathematical model or the differential equation for that typical process. We have also some other alternatives. Typically the water tank is a non-linear model, so then you can use this model. Here is another small-scale process model called the air heater, and here you find or see the differential equation for that specific system. So these are the kind of equations we are going to implement in LabVIEW. In this video we are going to implement the differential equations as block diagrams. So here we see a typical first order differential equation like this, and here you see the block diagram based on this equation. So here you have the integrator symbol, and here you have the feedback, and here you have the control signal like this, and all these blocks are available inside LabVIEW. So this is the structure we are going to make when implementing the modules inside LabVIEW. In the LabVIEW control design and simulation module, we have lots of built-in functionality we can use. So let's take a short look at these functions. When you install the control and simulation module in LabVIEW, you should see these new palettes inside LabVIEW. So when you right-click on the block diagram, you should find the control and simulation palette like this. So here you have functions for PID control. You have lots of different PID controllers you can use. In the control design palette, you have lots of functions to create and design models. And in this simulation palette, you have the simulation loop, which we will use, and you have different sub-palettes for different types of models we will use in our programming. Here we see a typical example in LabVIEW where we have used the control and simulation loop. We have created a block diagram of our model. We have implemented a PID controller like this, and then we can also plot the values in a chart like this. So such a system we are going to create in this video. So let's start creating our first example in LabVIEW. We are going to create this example in LabVIEW. Here are our first order differential equation, and here is the block diagram for that differential equation. In the simulations we will set a equals to 0.25 and b equals to 2. We will use the control and simulation loop, and we will implement the block diagram as shown here inside LabVIEW using the built-in functions. So for a and b we use the multiplication block like this, and the summation point we use the summation function. The integrator symbol we use the built-in integrator, and we want to plot it, so we use these functions in order to plot it. In order to do the simulation we need to set some simulation parameters. We will show how to do this soon. So here we also see the block diagram. So here we can set the control signal. If we set u equals 1 we can simulate a step response, and here we can set values for a and b on the front panel. So when we click on the run arrow we should see a plot like this. So let's do this simulation in LabVIEW. So now I have opened a blank VI in LabVIEW, so let's start creating our simulator. So let's start to find the control and simulation palette. We can pin it like this, so we have it there, and here we have the simulation sub palette, and then we can use the control and simulation loop like this. Next we can go to our front panel, click Ctrl E like this, and then we can create some numeric controls. We start with U, the control signal, and then we have the constants A, and we have the constants B like this. So A should be 0.25 like this, and B should be equal to 2, and then we can set U equals to 1, indicates it's a time step response. In order to save these results we can go to edit and make current values default like this. So let's go back to our block diagram. So we have, and you see when we created these objects on the front panel we got also a similar let's call it variables on the block diagram. So let's start to create our block diagram for this model. So here under signal generator we have lots of different signal generation, but in our application we need some signal arithmetics, so we need the summation, we need the multiplication, and we need another multiplication like this. We need a graph, so we find the graph utilities and use this sim time waveform like this, and then we need to find the integrator. So here under continuous we find the integrator and we put it here, and now we can start wiring these objects together. So here on input we have the control signal multiply with B, this, and here this should be multiplied with A, and this one should be multiplied with so this B should be here, and then we should put A here. So let's try to wire these together. So we click on the U and input here like this, and multiply with B, and then we wire it to the summation like this, and output should go into the integrator like this, and the output of the integrator and output of the process should be plotted in this chart. And then we have this feedback here. In order to do that, we need to change the direction of the multiplication block. So we just right click on it and select reverse terminals like this. So then the output here should be multiplied with B like this. And then the output here should be a feedback like this. So now we should be finished with our program. So let's go to our front panel. And we have also, when we created this functionality, the chart graph was automatically created by LabVIEW. Like this. Before we start the simulation, we can check our simulation parameters. So we right click on the control and simulation loop, select configure simulation parameters, and this window pops up. So here you have the initial time for the simulation, and here you have the final time for the simulation. As stated in the PowerPoint, you should have the final time equals 20. Here we can select different solvers you can use to solve the differential equation. You just use the default one, and here you have some other parameters you can set, the step size, etc. But you just leave them the way they are and click OK. We click Ctrl E to go to our front panel, and then we can start the simulation clicking the run button like this. You see, we got this nice step response. So we can just set or change the axis here. We can just double click here to select from 0 to 20, and then you see we get this nice step response. You could also try with some different values on A and B and see how that affects the simulation results. This was a very simple simulation example in LabVIEW. So this is the block diagram, and this is our final front panel on our graphical user interface. In the example we developed, we just simulated the mathematical model. Now we want to increase our program and introduce a PID control. So we want to control our process using one of the built-in PID controllers in LabVIEW. Here we see a typical control system. We have the process or a model of a process which we just implemented, and we have a PID controller, and typically we have a sensor with a feedback. So we have a reference signal, and then we have the error between the reference signal and the measurement, and based on the error the PID controller puts out a control signal to the process like this. Here is an example how we can do this in LabVIEW. So you see the block diagram we just showed can be identically implemented in LabVIEW like this. So we have our process here, which we just implemented, and then we have the PID controller, and here we plot the output of the process, and then we have a feedback, and then we have the control signal, the reference signal, and based on the error between the reference signal and the output of the process, and the PID controller find a proper control signal. We also need to set the parameters for the controller, the PID controller, and the KP, the TI, the integral, and the derivative time, TD, like this. In LabVIEW we have lots of different PID controllers. In the PID palette we have several PID controllers, like the PID Advanced, ordinary PID, and in the continuous linear systems palette we have also a PID controller, which we will use in our next example. So in this next example we will use the built-in PID controller in LabVIEW to control our process. So this is our program for the previous example. So here we just simulate the process, but now we need to replace the U with a PID controller. So here we see the front panel for this example. It's almost identical to the previous one. We can set A and B, but instead of setting the control signal is calculated by the PID controller we are going to use. But instead we can set the reference signal like this, and we can also set the PID parameters like this on our front panel. So here we see the code we are going to create. This is the process we already created, so we need to replace the manual control signal with the PID block like this, and then we need to add a new summation point where the error between the reference and the process value is calculated and sent to the PID controller, and based on that the PID controller send a proper control signal to our process. So let's create this application in LabVIEW. So we start with our previous example. So the idea is to replace the manual control here with a PID controller. So let's find the PID controller we are going to use. Here we have the continuous linear systems subpalette, where we found our integrator. Here we also find the PID controller block. So let's put that block on our block diagram. In addition, we needed one more summation like this. And then if we go to our front panel, we need to introduce the reference signal like this. So we just call it R or something, or yeah, R, like this. And then we go back to our block diagram and then put it here. Then we wire the output to the input of the summation point, and the output of our process, which is here, should be a feedback like this, and then the output should go to the error input of the PID controller, and then the output is the calculated control signal. So then you just need to remove this one, and then instead of having this as a controller, we can right click on it and change it to an indicator like this. So then we can wire like this, and output goes inside the multiplication block like this. And now if you click on our front panel, you see the background here has turned gray, meaning this is just an indicator. You cannot set the value, but the LabVIEW program or the PID block calculates the value like this. Then we are almost finished with our program. We go back to our block diagram. So the next step is to find or set the PID parameters. So then you need to right click on this PID block, select configuration, and then inside this configuration window we can set the PID parameters. We can set them directly here, or we can select them from outside. So then you choose terminal, and terminal like this, and then we can click OK. And then if you click Control H to get help like this, and click the mouse on the block, we see we have these three inputs on the PID block. So then we can just right click and create indicator like this, and then sorry, it shouldn't be an indicator, it should be a control like this. And next, TI, right click, create control, and then we have this one, and the last one, just make some adjustment on our block diagram like this. And the final should be this one, right click, create, and control. Then we have these three here, and they should then pop up on our front panel. So then we go to our front panel and see here we have those, the PID parameters like this. And then now we are finished with our program. We can start the simulation by clicking the run button. So let's start the simulation, clicking the run button like this. So let's start with now in this case the reference signal was 0, so if you set 4 or something, and then click the simulation once more like this. Yeah, so in the example we just on the plot we just remove the auto scaling on the y-axis, so we set from 0 to 10, and then we run the simulation like that, and then you get these typical simulation results where we have where the controller are able to control the process, so the output reaches the reference value, in this case 4, like this. So the problem with this simulation that is just that the simulation stops after 20 seconds, but typically we want to let the simulation run until we stop, we click a stop button or something. So let's see how we can do that. In order to do that, we need to change some of the simulation parameters in the configuration window. So the first thing we need to set is the final time. We set it to infinite. And also on the timing parameters we need to set enable synchronized timing, so we simulate in real time. So let's do this inside our simulator. So we change these settings, right click on the control and simulation loop, and select configure simulation parameters, and then here final time is set infinity like this. Here we can also change the step size to 0.1 like this, and then we have the timing parameters like this. So we select this option like this. So then we have changed this setting and this setting. We also in this case change the step size. So just click OK now like this, and then we should include a stop button. So let's go to our front panel and let's make or create a stop button like this. So a stop button, and the stop button need to be connected to the control and simulation loop. So when you click the stop button, the simulation should also stop. So need to find the proper block for that. So here in the simulation palette we can go to utilities and select the halt simulation block, which we put here. Then we wire our stop button to the halt simulation block like this. And now we can try the simulation one more time. We go to our front panel, click the run button to start the simulation like this. And then you see it's the simulation goes a lot slower because it's in real time. Yes. Before we start the simulation, we need to also set. If we go back to our configuration and the simulation parameters, since we set the step size here, we needed also to set the period to 100 like this. So now let's start the simulation. Also in this example I have changed some of the PID settings to increase the performance of the simulation and the PID controller. So let's start the simulation with these parameters. We use the same reference, and A and B is the same, so let's start the simulation. Click the run button, and then you see the simulation is in real time, and the controller makes the process go to the reference value, and the simulation goes on until we click the stop button like this, and then the simulation stops like this. So this is in this example we showed how we can simulate a process and control the simulated process using one of the built-in PID controller in LabVIEW. In our next example we want to introduce something called simulation subsystems, which is handy to use when the models we implement is getting big, or we want to use our model in different programs. So let's take a look at simulation subsystems, and in LabVIEW we'll show an example. So we start with our previous example, and the thing we want to do now is to take our process, which we have here, take that part and transform it into a simulation subsystem. So let's do that in LabVIEW. So here you see how it should be when we are finished. So here it was our previous process. So we have transformed the process into one single block called a simulation subsystem. So let's see how we can do that inside LabVIEW. So here is our previous example. as shown, this is our process which we want to transform to a simulation subsystem. So let's start to create a simulation subsystem from scratch. So we click on File, New, and in the New window we go to Other Files and select the simulation subsystem. And then you can click OK. And then we get these windows, and you see in this subsystem, you see the background color is a little bit different from ordinary VIs like this. So it's the background is more yellow, meaning it's a simulation subsystem. So in our case, inside here we should create our process. So let's just copy these functions from our main program into the subsystem like this. And then we need also this U. Like this. And now the U should be a control like this. So this should be an input to our process. An output. We need also an output here. So let's create that on our subsystem. So this should be inputs. And output should be a numeric indicator like this. So you can call the output X like this. And then we can wire X like this. And this is our subsystem for our process. So then we can save it. And then in the same folder, we just save the subsystem and call it process. And then click OK. Like this. And the next, we need to set the inputs and outputs of our subsystem. So then we can, since the U should be an input, you just click on the input terminals here and click on U, and then A and B should be in the input. So A, B should be inputs and X should be an output. So then we use one of the outputs on the right side like this, and then save it. And then we can just drag our subsystem into our main program like this. So here is our subsystem for our process, and then you can remove this part and replace it with our process like this. So here the input should be the control signal, and output is X, which we should plot in the waveform chart like this. So you see the results, that we get a much cleaner main program, and then we can also reuse our process in other programs. So let's run this program and see what happens. So we run it like this. Yeah, and you see, as expected, we get the same results as in the previous example. But in this example, we got a much cleaner main program using a subsystem. If you want to change the subsystem, we can just right click on it and change or select Open Subsystem, and then we can do the necessary changes like this. Next, we want also to create a simulation subsystem of our PID controller. So the code inside here should be a new simulation subsystem. So here you will see our final program. So here we have the PID controller, and here we have the process. You see the main program will be much cleaner than the original example. So let's create this example in LabVIEW as well. So we start with our previous example. So this is the part which we want to create a subsystem for now. So let's create a new subsystem from scratch. Select new simulation subsystem, like this. And then we just copy the code we need, like this, into our new subsystem, like this. So the input here to the PID controller should be the reference signal, while U should be the output. So we just need to create a new numeric controller like this, which should be the reference signal, and the reference signal should be an input like this, and the output from the process should also be an input to the PID controller. So in addition to R, we also need the measurement value. We call it in this case Y, like this. Then this should be connected here. Like this. So this is our PID controller implemented as a simulation subsystem, like this. So like we did for the previous one, we just need to set the inputs and outputs. So R should be an input, and then we have these could be an input, these PID parameters, like this. This Y should also be an input, and output the control signal, like this. And then we just save it, and you can save call it controller or something. You can call it PID controller, like this. And then we can use that PID controller in our main program. So we just drag it like this, and then we can remove this part, like this. And then we just wire the input here, the reference value, like this, and the output of the process, the feedback, like this, and the output of the PID controller, the control signal, should be an input to the process, like this. And then we have a much cleaner main program, like this. And then the functionality should be the same as the previous example. So let's start the simulation. So we start the simulation clicking the run button. And yeah, before we start the simulation, it's also a good thing to have to be able to set the PID parameters on our main program. So I just added these parameters as an input to the PID controller, like this, and then you can easily change them on our front panel. So let's start the simulation. And then you see the simulation results was as expected, similar to the previous examples. Just click the stop button and then we are finished. In our next example, we will replace the control and simulation loop with an ordinary while loop. Here we see the code for that. So we use instead of the simulation control and simulation loop, we use a while loop, and then we place our subsystem, our process, and our controller subsystem into the while loop, like this. So let's create this example in LabVIEW as well. So in our LabVIEW program, we just start creating a while loop, and then we just copy our functions inside the while loop. And this halt simulation cannot be used in a while loop, so we just remove this one like this. And the same with this function cannot be used in a while loop, so just remove it, and then we just mark our code and put it inside the while loop like this. So now we can delete this control and simulation loop and just use the while loop like this. And then you need to wire the stop button to the while loop like this. We want to plot it in the same plot. Just remove some bad wires. You can click Ctrl B to remove all bad wires like this. Then we have our controller, PID parameters, and then we have the reference signal like this. And the output should be an input to our process like this. And then the output of the process should be plotted like this. In addition, we need to have the feedback from the process into the PID controller. In order to do that, we wire from the output and find the Y like this. When we did that, this feedback node was created automatically like this. Like we did with the multiplication blocks earlier, we can just right click on the feedback block and change direction like this. Can just make the wiring a little bit cleaner like this. And like this. So now we have replaced our simulation loop with an ordinary while loop. Like this. So let's see if our simulation works as expected. So we use the same parameters and run our simulation. Yeah, so you see the simulation here is running very fast, so we need to enter a wait function inside our while loop. So just click OK, stop, and then outside our while loop, you just need to use the wait block like this. In this case, you can just right click, create constant, and then here we set the simulation time. So then you can use you can set 500 milliseconds like this, and then try one more time, and then you see we got these much cleaner results like we did earlier. So we have a little overshoot, and then finally our controller are able to make the process reach the reference value or the set value like this. When we are finished with the simulation, we can just click the stop button.